Hi everyone, welcome to my class of Basic Statistics for Data Science. So this class will serve as a starting point for you for your journey of data science, and from this class I hope you can learn different concepts and terminologies, and if you want to dig deeper into these terminologies and concepts, then you can easily do a research or learn more about these concepts. So the agenda of this class is that first I will discuss about what is hypothesis testing, then probability and how we can use probabilities, specifically p-value, to confirm or to reject your hypothesis. Then I discuss about how it works and the law of the large data, which is central limit theorem, and what is normal distribution and statistical significance and correlations. At the end of the class I will show a few examples of how one can use our app, Actable AI, to run correlations with different data sets. So hypothesis testing is actually quite a common thing in normal life. I think for us, each of us, we often come with different hypotheses, say, trying to explain for different things. For example, say like a baker can have a question about whether she should add cinnamon to her cookies or not, right? And then what she would normally do is that she will make a few cookies with cinnamon and then ask some random people to taste them, and then tell her whether they prefer them than the cinnamon than the cookies without cinnamon. Another example is that if we have a question, a hypothesis about running 30 minutes every day in a month will help losing weight. And then if we have this hypothesis, then we can go and ask random people to run 30 minutes every day, and then in a month, after a month, then we can collect the data about their weights and compare that with the ones who don't run, who didn't run in the last month. So this might sound simple, however, when the sample size is small, simply comparing the averages of the sample population is usually not enough. The reason is that if the sample size is small, then the difference can happen by chance. So we don't know that whether the phenomenon actually comes from from our hypothesized effect or not. So that's why that we need hypothesis testing. So in a hypothesis testing, we would normally have a null hypothesis and an alternative hypothesis. So a null hypothesis is when there is no effect. There's no effect or whatsoever, right? So if the null effect is true, then usually the observed difference between two groups should be smaller or close to zero. Meanwhile, if the alternative hypothesis is true, then often the observed difference between two groups should be larger than in the null hypothesis. Right? For example, in the example of our baker, then an example of the null hypothesis is that adding cinnamon doesn't make people like cookies more or less. Right? And the alternative hypothesis is that adding cinnamon makes more people like cookies. So in order to do hypothesis, we need to understand what is probability. So probability actually is something perhaps everyone knows and understand about. It's simply just a chance of something that happens, right? So example are chances of rolling a dice with number 1 is 1/6. chance of winning jackpot Euro millions is teeny tiny low, right? Or a chance of a random person being older than 100 years old in 2021 is about 0.004%. So that is probably simply just a chance of something that happens. So going back to the hypothesis, then we need to know, given the data is small, then we need to know what is the chance of our collected data to happen to look better, or even without any effect, right? For example, if we survey only 5 people who taste the cookies with cinnamon, right? And what would be the chance of 3 out of 5 people or more would say they prefer the cookies with cinnamon than without cinnamon, even though cinnamon doesn't add any effect to the cookies. So that is come to p-value. So p-value is the chance of the observed effect to be at least this extreme under the null hypothesis. So for example, in the case of our baker, then if we survey 5 random people, and 4 out of 5 random people say they prefer cookies with cinnamon, then p-values is a chance at least 4 out of 5 random people prefer cookies with cinnamon. Another example is that if we survey 5 random footballers, right, 5 random footballers, and their average height is 6 feet, then whether are footballers taller than an average person. So in this case, the p-value is the chance of 5 random people's average height is at least 6 feet. So in summary, p-value is simply the chance of the observed effect, right, or more extreme under the null hypothesis happens. So if p-value, if the chance is very small, right, typically less than 5%, then it means that the observed effect rarely happens by chance, right? Then in this case, we can reject the null hypothesis, and then we can say that the alternative hypothesis is statistically significant, right? So, but how can we calculate the p-value? So that is when the central limit theorem comes to save the day. So the first part of central limit theorem says that if we take sufficiently large random samples, normally larger than 30, from a population with replacement, then the distribution of sample means will be approximately normally distributed. And what does it mean by sample with replacement? And what does it mean by normally distributed? Then I will explain these terms in the later slides. So next, I'm going to show what is normal distribution. And this is actually a distribution, a probability distribution that happens quite often in real life. So here I'm going to show a video of a Galton machine that basically a machine that have like the pins arranged in this alternative shape and alternative orders, right? And then you have like different slots here, and then you drop a lot of small balls into this machine, and then this ball will randomly distributed in different slots, okay? And after a while, when enough balls are dropped, then we will see that this ball will distribute in this blacker shape, this bell curve shape. So when this converge, and when there are enough balls dropped into this machine, then we see that there are more balls in the center than both on the left or the right hand side. So as you can see that the balls are building up to be in this shape. Right, so that is a normal distribution. Right, another example of normal distribution that happens in real life is if we look at the height distribution of women and men, then we can see that the height of women are also distributed in this bell curve shape. We have the mean here and then different values on the other side of the mean. Similarly, if we look at height distribution of men, then we also see that they distribute in this bell curve shape. So that's also an example of normal distribution in real life. Another example of normal distribution in real life is the distribution of the ACT score, which is used for the college admission in the US. I think it's ranked from 1 to 36 or something. So here we also see that the ACT score also distributed in this bell curve shape. We have the mean and then just two equal sides on the left and the right. So that is ACT score distribution in 2005. So in summary, normal distribution is a distribution where we have a mean, right, and two equally distributed on the other side of the mean in this shape, in this bell curve shape, right? And the bell curve shape has a width. Width is and it's defined by standard deviation. The standard deviation is basically half of the width at this here. So here the distance here is basically one standard deviation. And let me remind that standard deviation is square root of variance. So this is one standard deviation. So basically, this figure says that in the range from mean minus one standard deviation to mean plus one standard deviation, then the data, 68.2% of the data distribute in this range. The chance that the data will fall into this range is 68.2%, right? Or the chance that the data point falls into this range from mean minus 2 standard deviation to mean plus 2 standard deviation is about 95.4%. Okay. So, but this is normal distribution. Here I'm gonna explain what is sampling without replacement. So sampling without replacement is when we draw a sample from a population, then we take it out of the population, and that sample will no longer be drawn in the next time. So here, for example, we have initially we have this population, right? And when we draw 5, then 5 will be taken out of the population, and it won't be you won't be able to draw it again. So here next let's say we draw 7, right? And 7 is taken out of the population, and won't be sampled again. So that is sampling without replacement. Vice versa, sampling with replacement is when you draw a sample, but you still keep it in the population. And you can still draw it again. Next time. So here we sample 7 still in the population. Sample 10 still in the population, and 5 here, 5 can still be drawn again. Okay, so that is sampling with replacement. So the first part of central limit theorem says that if we sample a sufficiently large number of data points, which is more than 30 data points, with replacement, then the mean of this sample will distribute it in under normal distribution. So that is the first part of the central limit theorem. The second part of the central limit theorem saying that this normal distribution, I mean like the so here let's say on the right hand side we see like here for example we have like this is the distribution of the population. It has a mean here, right? And then say these are different sample set, okay, different sample. If you take sample, that can be different sample. If you do multiple times, then you can have different samples, right? Different sample. Each sample has a mean. Let's say SA, SB, SC, and SD here. And the second part of the central limit theorem saying that the mean of the SA, SB, SC, and SD is actually equal to the mean of the population. So MX is the mean of this X, A, S, B, C, S, D is the same as the mean of the population here. Okay. It also says that the variance of this distribution, which is square of the standard deviation, of this distribution, is equal to the population variance divided by sample size. So this variance, the variance of the distribution is equal to the variance of this distribution divided by the sample size. So, however, in reality, the population's variance is usually unknown. So in this case, we can actually use the sample variance, the sample variance for an estimation instead. Okay. So that is the second part of central limit theorem. So looking back at the is the example of our baker, then under null hypothesis, right, 50% of people prefer cookies with cinnamon. So this is the null hypothesis. So to test if cinnamon actually makes more people to like cookies, then we randomly pick 30 people to try the cookies with cinnamon and tell us if they prefer it or not, right? And so we survey these people and we see what the collected data is. And for example, if the collected data show that 20 people say yes and 10 people say no, and basically what we have is a sample size of 30, right, which is enough to satisfy the central limit theorem. And the mean, let's say if yes is 1 and no is 0, then we have a mean. The mean here is like 67% of them saying yes. So here under the null hypothesis, here we have the mean. Here is like 50%. We know that that this observed sample mean will distribute in the normal distribution, right? And under the null hypothesis, then it will have the mean of here with 50% under null hypothesis. Okay. So if the null hypothesis is true, then the observed sample mean will distribute in this bell curve shape, okay, with this mean. So here is a actual observed sample mean, 67%. 67% is the actual observed sample mean. So here p-value actually the area of this yellow part, the area of this yellow part, which is the chance of the observed sample mean to be at least like 67%. So basically, here I remind again that p-value is the chance of at least 20 out of 30%, 20 out of 30 people prefer cookies with cinnamon under the null hypothesis. So here we see that if p, the smaller p-value is, then the rarer the observed data under the null hypothesis happens, right? If it's more to be on this right-hand side, then the chance of this observed data happen under null hypothesis is really low. So when it's rare enough, typically in scientific literature, we pick 5% at the threshold. When it's low enough, then the difference between the sample mean and the population mean is statistically significant, right? And then in this case, we can start to reject the null hypothesis. Um, and then we can accept the alternative hypothesis, which is like adding cinnamon makes more people like cookies. But that is statistical significance. So basically, that's simple. So that is a case of when the data size is larger than 30. So what if like the sample size is small, and it's hard to get more data, it's expensive to do that, then it depends on the type of the data, the population distribution, etc., etc. I will give another class about hypothesis testing when the sample size is small enough, but for now, our customer can schedule a meeting with our data scientists if they want some advice on this. So one thing we need to be very careful when doing hypothesis testing is data dredging. So data dredging is when we try hard to find a statistically significant hypothesis by performing different or multiple hypothesis testing on different subsets of the data. So there is a popular example on SKCD. Here we have, like on the right hand side that I show here, we have two scientists examining the link between jelly beans and acne, right? So they want to check whether having jelly bean cause acne or not. So sorry, linked to acne or not. Then first they do a hypothesis to see whether jelly bean is linked to acne, and they didn't find anything. So they didn't see any statistical significant difference between people who have jelly bean and people who don't have jelly bean to have acne. The chance of them to have acne are not different. At first they didn't see any link, right? And then they start to look at different subgroup of the jelly beans as they have a multiple color, and then they start to look at each subset of the jelly bean with different colors. So they start from red, green, yellow, blue, etc., etc. And then at some point they find a color. They find a group of jelly bean with a certain color that has a very small p-value. And then they make a conclusion that say green, for example, green jelly bean is linked to acne. So this is wrong. This is not how we should do it. Okay. Remember that p-value is the chance of the observed effect to be more extreme under the null hypothesis. So even if this chance is small, but if you do multiple hypothesis testings with different hypotheses, then the chance you find one with small p-value is still very significant, right? So try to avoid data dredging as much as possible. It's a best practice to come up with a hypothesis first, and then go collect the data, and then just use the data to confirm that hypothesis. So try to avoid collect the data and then come up with different hypotheses. So if you have to do that, then try to adjust the p-value threshold accordingly. For example, you can divide p-value threshold by the number of tested hypotheses, so we can reduce the chance that we are testing multiple hypotheses. So that is data dredging. So next I'm going to talk about correlation and why that we want to learn about correlation. So basically correlation is when we say that A and B are correlated when we observe B changes when A changes, right? So that is correlation basically. So this is perhaps something that everyone knows, is that correlation doesn't mean causation. The reason is that because maybe both A and B can be caused to change by something else, right? So never make conclusion about correlation is a causation. If you want to learn more about how to infer causation, then I would recommend you to attend my class of causal inference, then you can see how you can do causal inference with our application. So there are two common types of correlation. The first one is Pearson correlation, that indicates the linear relationship between two variables, linear relationship. So on the right hand side, the red line here is an example of a perfect Pearson correlation, where we see that the data point increasing linearly here. Spearman correlation is the correlation that indicates a monotonic relationship. So it doesn't the speed of B changes when A changes. It doesn't have to be the same as in the case of Pearson correlation to be perfect. So here on the right hand side we see an example of a perfect Spearman correlation, that as long as like B increase, while when A increase, then we have a perfect Spearman correlation, right? Doesn't have to be at the same speed as in Pearson correlation. So that is Spearman correlation versus Pearson correlation. So there's some differences between Pearson correlation and Spearman correlation, but one thing you might want to notice is that Spearman correlation is a lot less prone to outliers than Pearson correlation. In Pearson correlation, one or two outliers can make the Pearson correlation skewed and doesn't really reflect the true relationship between data points. So now I'm going to show some example of how to find correlation using Actable AI. And here I have a data set of COVID mortalities in different states in the US, right? For each state, I have the mortality rate in July 2021. I also have different attributes like stringency index, like how strict the measures are in each different state. Also the population, right, or population density, or the obesity rate, or number of nursing residents per 100,000 people, median age, our Gini coefficient, which is inequality index, etc. So I want to see what are correlated to mortality rate in different states. So here all I need to do is basically I select mortality rate, death rate per 100,000 people as a correlation target, and then I just select everything else as a compare factors, and then I click run, and after a few seconds or minutes, then you have the result here shown here, where we see that inequality index is highly correlated to mortality rate. So this is an example that featured on The Economist, that a data scientist from MIT found that this inequality index somehow is highly correlated to the mortality rate. The next is number of nursing home residents per 100,000 people, right, or population and density, etc. And all of these are statistically significant. So here we return only statistically significant result. So that is correlation, and here below you can see the distribution of the data point and also the coefficient, Spearman correlation, and how the data points are distributed. One can also do a control on different factors. Say, for example, if you have a question about what if we just look at the states that have similar population density here, then I choose here, for example, I choose population density as a decorrelation factor. Then you click run, and then here we try to resample the data so that the selected data are selected randomly, but also don't have this correlation in the population density at all. And then when we have this population density control, then we see that other factor disappear from the correlation because they might just be correlated to population density, right? And now we have only that inequality index, and the number of nursing home residents per 100,000 people are significantly statistically significant to the mortality rate. So that is correlation with network control. Another example of the correlation, here we show a correlation of different factors from age to like gender, race, relationship, etc., with whether someone has an income more than $50,000, right? So here we show that somehow someone is never married is negatively correlated to the fact that they earn more than $50,000 or not, and or if someone has like more education number, then they're more likely to earn more than $50,000. So that is correlation. And here, same, if you control by age and gender, then the correlation are no longer the same as before. But we see that when these variables are controlled, then we see that capital loss or never marry become more significant, or capital gain, etc. Right? So that's it. So that is the end of my class, and just want to give you a good news is that this correlation is free to use on our app, and we also have a different statistical tool as well, which are also free. So feel free to check it out, and let me know. Send me a private message on LinkedIn if you have any questions. Right, that is the end of my class for now. Thank you very much for watching.